Ellery. I work at Met Service, which is New Zealand's national weather forecasting agency, where I am a geospatial specialist. And my talk today is on bathymetry data wrangling. So at Met Service, we're mostly known for our atmospheric models. However, we also run ocean models to model and forecast waves, swell, currents, things like that. So this is some of the things we do and outputs we provide to clients in the public. And all of these things have a common input, and you may have already seen this from the technical problems this morning. Bathymetry. So we need a model of the surface of the seafloor. So bathymetry is submarine topography, meaning we're measuring the depth of the sea floor relative to the sea surface. And there's many ways we can go about measuring those depths, the simplest being dropping something heavy on a string and measuring how far that string goes. And the data can be in quite a lot of different formats because we can collect it in so many different ways, which makes it interesting to work with. So why is it tricky to produce bathymetry, to measure these depths? Well, we have water, which kind of gets in the way of some of our land-based methods of surveying topography, such as lidar and photogrammetry. So once we get into the water, our lidar can't necessarily penetrate very deep, and our photogrammetry only takes a photo of the surface, not underneath, so that doesn't work either. So we can move into using bathymetric lidar, which operates in the green band of the electromagnetic spectrum rather than the red, so it can penetrate a bit deeper. However, this only works in kind of shallow, clear waters, so only really in that coastal zone and not in all coastal zones. If we can also try to be a bit fancier and do correlations between the optical reflectance of the water and the depth. However, this relies on actually having some training data, some measured depths that are correlated to optical imagery colors. But again, this only kind of works in that shallow, clear, calm areas. Another thing we could do is use SAR data from satellites to correlate the shape of waves to the depth of the water. It's a bit above my pay grade, I would say. But we can go out a bit further into that kind of 50 meters off deep, kind of further offshore range. If we have a boat, we can go collect some multibeam or single beam echo sounding data. So a single beam is just sending a pulse of light down and measuring the depth via when it bounces back up, kind of similar to lidar, but underwater. Multibeam is taking a swath, so a measurement, not just a single column, a transect essentially, so that we can cover a wider area. But again, we can only really operate to about 500 or so meters. Once we're in the really deep ocean, we have not very many options. The most common, and what is surveyed most of the ocean with, is satellite altimetry. This is really coarse measurement. It's quite generalized. So it's not going to give us a very precise look at what the topography, actually the shape of the topography. If we have a lot of money, we could get a submarine, but I don't know how practical that is in most situations. So kind of as a result of this problem, our ocean is still largely a black box. This is the mapped areas of the ocean as of 2024, I believe. And it's about 26% of the seabed has been mapped to what's called adequate resolution, which is defined as 100 to 800 meters, depending on kind of how deep the ocean is. We generally don't care about having fine resolution when the ocean is really deep. But this is quite coarse still compared to what we see on land, where we've mapped all land areas to at least 30 meters resolution, and in a lot of places quite a bit higher than that. There is an initiative, a global initiative, to fill in these gaps by producing a definitive map of the ocean by 2030. Hopefully we can get there. Something you may be kind of wondering is, you've seen maps that look like they're all filled in. They don't look like this when you look at a global map of the world's oceans. And that's because a lot of areas have been filled in with either interpolation or altimetry data. So if you look, this has been scanned with multibeam, and these areas have been filled in. So they don't look quite as detailed. And it's quite obvious if you make a hillshade of, say, the GEBCO global grid, you really can tell what areas have not been surveyed with direct measurement methods like multibeam and single beam. So what does it look like around New Zealand? All of these, the blue areas have been surveyed with direct measurement methods, and the green areas have not. So we've done a pretty good job on the East Coast, but the West Coast is still a bit of the Wild West. That's 2021, 2022, 24. So we're getting better, but we still have quite a ways to go. So because the ocean is such a black box, and we've got all these different types of measurements, and some are direct, some are indirect, some are point, some are gridded, there are some challenges when working with that data, which contrasts a bit to maybe working with elevation data, especially in New Zealand, where you can go to Lynn's data service, download 1 meter lidar, it's all in the same projection and resolution, and it's great. So some of these include the following. So oftentimes we have higher quality data and lower quality data. So in this case, we have some 1 meter lidar on the land. We have some coarser resolution bathymetry. How do we merge these two together? And what do we do at the boundary between such data sets? They might be conflicting in what elevations or depths they say. We often are merging together both gridded and point or contour data sets. So in this case, we have some ENC electronic navigation chart data. We want to merge that in with the gridded data. How do we do that? What kind of makes sense to do? You don't really want to just extrapolate those single point values across a large area. It will look weird. A thing that doesn't get talked about quite so often is that a lot of hydrographic or bathymetric data has been captured for navigational purposes. So it's often shoal biased, meaning that it's conservative in its estimate of depth because we don't want ships to run aground on reefs or other things. So it may not be appropriate for use in, say, models where we don't want that bias. We want the actual depth of the water. How do we fill in those missing gaps? Do we use a smoothing algorithm? It's going to look, in this case, it looks quite weird when we interpolate it. You get a lot of artifacts. It's not very nice. We don't know that much about how frequently the seafloor changes. So in producing this definitive map of the seafloor, we're not really accounting for how frequently we should update that over time. We don't know that much about underwater landslides, in a lot of cases dredging, things like that. So I've just overlaid a different data set on top of the other one, showing some dredging going on. This is a port. And then another thing we often do is kind of coarsen the data, but how coarse are we going to go? Are we going to overgeneralize the terrain? In doing that depends on the application. And then bathymetry data often comes in lots of different formats. Most commonly I get it in XYZ with not very much metadata. So working out what is the projection, what is the vertical datum. When we're running ocean models, we want to run at present day mean sea level. So you could have a data set that's in mean sea level, but it could be 10 years ago's mean sea level. So mean sea level is not like a constant value, it's changing over time. So how do we include that as well, given the sparse kind of network of tide gauges around the place? And then, yeah, kind of following on from that, we lack geographic metadata and documentation, and our gridded products that, such as GEBCO and stuff, I'm not sure how those are necessarily produced. The documentation is a bit hazy, so it'd be good to have more documentation out there when we make nice grids. All right, so the point of this slide is that doing all the things from the previous slide is really hard in desktop GIS, and it is a lot easier when you use scripts such as Python, and these are some of the packages that I find myself using quite often. So 2 common scenarios that I come across in dealing with bathymetry data are fusion, meaning we're merging, combining multiple data sets, we're fitting the puzzle pieces together, which could be topography bathymetry, it could be a higher resolution survey, lower resolution gridded data set, and something that's really important with ocean modeling is if you have an edge, a sharp edge between 2 surfaces, that's going to show up as an artifact in your wave or whatever model. And it's expensive and takes a while to run those models, so if I get the bathymetry wrong, it costs money and is annoying to have to rerun the model with a better bathymetry. And the other scenario is interpolation. So rather than having our 2 puzzle pieces, we have to draw in the second puzzle piece. So how do we fill in the gaps? That could be kind of interpolating between points in transects or contour data, filling in the voids when we don't have anything at all. So a couple of fusion methods. So the most simple would be to just stack them on top of each other. So take a new survey, throw it over the top of your old survey. As you might notice, this will lead to an edge effect, which is bad for running models. A better method is to do some weighted blending. So I found this paper a while back, and that involves having a variable blending overlap. So if our new survey is a lot different to our old survey, we have a wider overlap. If they're quite similar, that overlap can be small. And between that overlap, we take a weighted average of the 2 models. So what does this look like with real data? This is a coarse resolution topo bathy merged data set. We want to overlay some new topography that's really high resolution. If we just put it on top, it looks really bad, and that coastal zone is not going to be very well resolved. If we do weighted blending, we can get something more like this. So you can see that in the estuary, the overlap is a bit smaller because the data sets match up pretty well, whereas in that area kind of around the coast, they don't match up well, so we have quite a big overlap. There's still some artifacts in this, but it's pretty high up, and so it wouldn't matter for an ocean model because we're not going to care about the elevations that high up. And yeah, I've used that quite a bit, and it works well. Another method that I came across on this website is to preserve the coastline. So if we have a high resolution data on the land and then a pretty coarse resolution gridded data set, we want to preserve all of the values on the land and only kind of adjust the coarser resolution. What we'll do is take some fixed distance offshore from the land and then take a weighted average, take a line and then take a weighted average of the gridded data set with that line. So you do get the shapes kind of coming through of the gridded data set, but it matches up with the high resolution model. All right, some interpolation methods. Don't necessarily need to talk about these super detailed since this is a GIS conference. But, you know, we go from simple interpolation through to complicated interpolation, and depending on the application, if you're processing a lot of data, you may want to go for something simpler, kind of depending on the use case and how much time you have. But something I've come across that is a good balance between simple and slightly complicated is an adjusted inverse distance weighting method. So inverse distance weighting on its own is used quite a lot across science fields, and that just involves taking a weighted average of nearby points. So if our pink point in the middle is the interpolation point, it's going to be created by taking a weighted average of all those points around it, but weighting the closer points more than the further away points. Adjusted inverse distance weighting accounts for shielding, meaning that if you have some points that kind of shield further away points, those further away points are no longer included in the weighted average. So those yellow points way far away are shielded by the pink, light pink points, and thus they're not part of the weighted average anymore. And so what does this look like in terms of the shapes we kind of get out of the interpolation? With inverse distance weighting, we get this bullseye effect. So our middle point is our interpolation point. It's taking a weighted average of all of those points, including those really big values that are further away. And as a result, you end up with these bullseye sort of contours. With the adjusted inverse distance weighting, we're no longer taking into account those further away points. And so our center point looks more like the closest points to it, and our contours no longer look like bullseyes. So what does this look like with real data? This is some bathymetry, the white areas, there's no data. What we're gonna do is sample 5% of all the grid cells and do an interpolation based off that. Inverse distance weighting gives us this. I've put a hillshade on top of it so you can really see the terrain texture. It doesn't look very natural. Adjusted inverse distance weighting gives us this, which looks a bit more natural. And that's the original. Do the same again. We take fewer points, only 0.5% of the cells. Inverse distance weighting looks like that. Adjusted looks like that, which is a bit better. All right, so the last thing is thinking about texture. So all of the kind of mathematical interpolations end up generalizing, smoothing the terrain. And so I've been kind of like thinking about this quite a lot. You can see that here with the GEBCO grid. You can see all of the smooth areas have been interpolated or filled with those indirect methods, and it's really obvious compared to the directly measured data. So I applied this method called DEM fill, which uses machine learning to fill in the gaps. So this is our original data. We're just going to take big chunks out of it this time. Inverse distance weighting gives us this. Adjusted inverse distance weighting gives us this, which is not very nice. Nearest neighbor gives us that. Linear interpolation, that. Cubic. And then our DEM fill gives us that. It creates some new features that definitely didn't exist before, but but this is the original. It at least looks more like the terrain. Need to explore it a bit further, but it is kind of cool. All right, that's it. Thank you.
Thank you. We have time for one very quick question. Got there at the back.
Yes, you're okay. Then you get a different datasets. Can you also explore, I guess, the performance of your interpolation? Because that's something that if you're... So my question was, have you explored performance of different methods for interpolation, as the ocean's big, and
Yeah.
some of these models you need, decent resolution,
For
so it can
sure.
take forever.
Yeah. I guess a lot of the projects I've applied these methods to are kind of smaller contained areas. But yeah, I know from experience that applying something that's not like inbuilt into GDAL or something will take way longer. The DEM fill thing with the machine learning takes quite a while. I wouldn't necessarily apply that over all of the ocean. But yeah, I guess I'd have to go back and look at the code, but with the adjusted inverse distance weighting, I think I got it to be mostly implemented with like NumPy, so it was pretty fast. It's fast enough for everything I've used it for, I guess, yeah.
Thank you, Honorine, again.